Swayam Prabha. Digital India. Educated India.
So we start focusing on control affine systems. Like you said, it's affine because there is no control connected to this term. So it's not even linear in the sense linear is defined. Alright. We assume, because we are interested in looking at equilibrium, the origin as the equilibrium, we definitely assume that there exists a equilibrium control, if you may, yeah, such that this happens. Okay. So we assume existence of a u bar such that f0 0 plus summation of ui bar fi 0 is actually 0. Okay. So we assume some equilibrium control existence also. Okay. Why did we do all this? Because we could not get a nice smooth feedback that we were looking for. Okay. So at least C1 feedback that we were looking for. We only got a feedback that was C1 and everywhere but at the origin. Okay. At the origin we had, we had this lack of differentiability. Alright. And it so turns out, I mean, you can try different examples, you can try different controls here for this particular example. It so turns out that for this kind of a system you will never get a feedback law U which is smooth at the origin, C1 at the origin. Okay. So in order to give conditions for nice smooth controllers also at the origin, because origin is actually a point of interest, we do want to go to the origin, we had to specialize to control affine systems. Okay. That is why we are looking at control affine systems. Alright. We state an equivalent version of the control Lyapunov function definition, yeah, for control affine systems. I say this is equivalent for this system and we will actually prove one half of it, other half is actually an exercise. Yeah. How do we redefine control Lyapunov functions? The first one is still the same. It requires a function to be a candidate Lyapunov function. Yeah. So this is still the same, exactly the same. Alright. Now the second condition is where things change, yeah, for the control affine case. If this statement basically says that if the contribution of the control terms is 0, yeah, if the contribution of the control terms is 0 to the right hand side, then the drift term has to give negative v dot. This is what this is saying. These terms are what are connected to the control, right? When I take v dot, I will get del v del x f0 plus ui del v del x fi, right? Basically this expression that you see here on the left. Okay, you have del v del x times f0 plus ui multiplied by del v del x fi. Okay, so del v del x fi are the terms that give you the control movement due to the control. Now if it so happens for some x that all these terms are 0, then the control cannot move the system, right? In that case we require that the drift itself moves the system in the direction of the equilibrium. Okay. So when the control terms do nothing, then I need this term to act and give me a negative quantity. Okay. So that is what is this saying. Okay. How is this equivalent? I only prove one side, like I said. I will assume this and prove the previous one. Okay. The other way around is the exercise. So if I assume this, what am I saying? Let us choose an x bar such that this happens for some non-zero x bar, of course, x bar is non-zero, right? This is what is this assumption, okay, and I have for this particular x bar I have that this happens, right. But then things are after that it's very easy, right, because if this guy is negative and this is 0, this entire expression for v dot which we had in the first theorem, right. In the first definition we had del v del x fxu, okay, and what is del v del x fxu in this case? It is precisely this guy, yeah, del v del x f0 plus summation ui fi, right. So, if there is no contribution from this guy, so this guy is 0, but then by this assumption I already have del v del x f0 is negative, so therefore this guy is negative, okay. So, even though I am not actually taking any infimum over u, taking any infimum over u is pointless in this particular case, right, because del v del x times fi is 0, yeah. So, there is no effect of the control at all, but the drift term gives me a negative outcome, which is what I need, okay. Now, the other case where these terms are not 0, what happens if these are not 0? Okay, the only two possible cases are this, at least only two possible cases are this is 0 for all I, okay, and the other possible case is for some I this is non-zero, for some I, at least for some I this is non-zero, that is the other possible case. There are only two possible cases. So, what happens if del v del x fi is non-zero for some I? It is pretty straightforward. See, look at this again, this expression of the v dot for some x star, okay. If I just think of one control, just to illustrate that there is only one control vector field, then this expression looks so, alright. Now I already, so then if I expand it, I have this guy, okay. If I expand it, I just have del v del x f0 plus del v del x f1 times u1, but I have already assumed that this is not 0 anymore. We have already covered the case when this is 0. So, now this is not 0. If this is not 0, I can choose a control like this by inverting this guy. So, I inverted this, cancelled this and inserted a negative quantity, some negative quantity minus alpha, yeah. So, therefore, if you compute v dot in the like in the previous definition, del v del x fxu turns out to be negative, okay. So, I have actually given an expression for u, yeah, okay. Even if you had multiple controls and multiple control vector fields, I know that for one I at least this is non-zero, for one I this is non-zero, then I will just make that ui to be this guy, everything else I will keep it at 0, all other controls will be 0 and I will just choose ui as this expression right here, okay. So, then I have negative contribution, I am done, okay. So, this is how you can prove that this definition implies that definition for control affine systems, okay. The other side, that is the first definition implies this definition for control affine systems, is what is the exercise that you have to prove, okay. Should not be too difficult. Now, we have still not reached where we want to, yeah, we still do not have this way of constructing nicer controls, okay. We still do not have a way of constructing the nicer controls, okay, that are smooth at origin and things like that, okay. We are still not there. So, for that in fact we need something more, yeah. We are already at control affine systems, yeah. We need what is called the small control property. So, most of this work is due to Hartstein and Sontag, yeah, and in fact the references are also here. So, they actually proved all these results. You can see the years, it is 83, 89, so not too recent actually, yeah. So, they sort of came up with this notion of small control property, which is actually a strengthening of this control Lyapunov requirement, if you may, for control affine systems. What does the small control property say? It basically says that if your state is close to the origin, then your control also should be small. Okay, very reasonable requirement. It just says that your system should not be ridiculous, that even though you are very close to your equilibrium, you need very big controls to bring it back to the equilibrium. Okay, so that's sort of what it says. So how does it, again, whatever we say in words, we try to write in the math, epsilon, delta kind of thing. That's what this is. Okay, it says for all epsilon positive, there exists delta positive such that for non-zero x in the delta ball, there exists some control vector which is epsilon close to the equilibrium control and v dot is negative. Okay, and v dot is negative. I hope you see that this is stronger than the control Lyapunov condition. Okay, why? Because in this inequality it should be evident that even if all of these are 0, this is still required to be negative, and that was the control Lyapunov condition, right? The second condition was the control Lyapunov condition. The first was just positive definiteness, so that is anyway, there anyway. Okay, so the second, the control Lyapunov condition, this is stronger than the control Lyapunov condition. Okay, this implies the control Lyapunov condition. So we need this condition to state any result on nice controls. Okay, and like I said, this is a very obvious result, but we will still try to look at it with some nice, very, very interesting example. I mean, these guys come up with very fun examples, I can tell you that. They can come with a counter example actually. If you look at this system, x dot is x plus x squared times u. Okay. Now, I hope it's sort of evident to you that if I try to construct a control, forget v and so on and so forth. There is no, there is a v here, sure, but here we are not talking about a v. Okay. Suppose I want to construct a stabilizing control here, alright, close to the origin. You can see that first of all I will need a negative x. So basically this term has to contribute something like a negative 2x. One possibility. If this term contributes a negative 2x, then I have x dot is minus x and I know it's a stable, it's going to go to the equilibrium, right? Good to go. The only issue, if I make this minus 2x and I try to compute a control out of it, I may not be able to divide by x square all the time, but the point is I will still have 1 by x type of a thing happening in the control, right? Okay. Or if you look at it in a different way, whatever control you have here is being scaled by x square. So when you move far from the origin or slightly far from the origin, the control effect is significantly multiplied. But as soon as you come to x less than 1, okay, as soon as x becomes less than 1, you start getting closer to, or norm x or absolute value of x becomes less than 1, you start coming closer and closer to the origin. Yeah, the effect of the control is significantly shrunk. Yeah, significantly shrunk. Okay, so even if you try to apply a minus 2x out of this or anything that even tries to cancel this minus x, this x with a minus x, you will still have something like a 1 by x happening, and that is why the x squared, very specific purpose. So what does it mean? It means that you will keep having to scale up your control as you get close to the origin, right? As you get closer to the origin, control will have to be scaled up further and further. Okay, I hope you are convinced. So u is large for small x, first thing. Second thing, when x is negative, you have to push it in the positive direction. So this has to be positive. So control has to be positive. So negative x, positive control. Similarly, positive x, negative control. So what have we concluded from these 3 points? Control is large for small x. In the positive direction, control is negative. In the negative direction, control is positive. So what happens as I come closer and closer to the origin? You see what I have just drawn here, exactly this. Here you have big control, big positive control, big negative control. Got closer, big positive, bigger negative, even closer, very big positive, very big negative. So you can see what's happening. This cannot be a continuous control at all, right? As you get closer to the origin, control will explode in the opposite directions. Yeah. So I mean, it's not even a very scary looking example. I mean, it doesn't look scary off the top of the just looking at it doesn't look that scary, but it is. Yeah, it's a very bad system that you can't design continuous controllers for. Okay. So this is sort of the example. So this sort of a system does not satisfy a small control property. Yeah, because even if you are close to the equilibrium, you are not going to get this kind of property. Impossible. You are going to get very large controls. In fact, I mean infinite control if you get very close to the origin. Yeah. Okay, unbounded controls. Okay. So that's maybe one of the reasoning why this seems like a reasonable assumption, that if you are close to your equilibrium, you should require less effort. Yeah, nothing very bad should be happening with the system. So this is a very reasonable sort of a control continuity assumption. Okay. Okay. So if you do have such a small control assumption, then you have this very strong result called the Arnstein-Sontag theorem, and this happens to be a constructive result. In fact, one of the few constructive ways of coming up with a control law if you are given a control Lyapunov function. Okay. So what does it say? This is called the Arnstein-Sontag theorem, or the the corresponding control law is called the Arnstein-Sontag universal formula. Yeah. What does it do? It says if you have a control affine system, just like we saw, and if there exists a control Lyapunov function for the control affine system, then the system admits the small control property if and only if it admits an almost C infinity stabilizer with u0 equal to u bar. Okay. So very strong result. Why it's a very strong result? First of all, it's an if and only if result. Yeah, in typical mathematics and applied mathematics, if and only if results are considered very strong results because they are very tight. Yeah, it's like this implies that and that implies this. So you can't have one without this. It's a very tight result. Yeah. So it says basically that the assumptions that you made are the least required for you to have a control like this. Yeah. So these are good. These are considered very good results. The other thing is, because this is constructive, we will look at it later. It actually gives you an expression for the controller. Okay. Now the only sort of fine point to see is that it says that it admits an almost C infinity stabilizer. Okay. You already know C infinity would mean smooth. Okay. And you know what is a stabilizer? Stabilizer just means that the control will make you asymptotically converge to the origin. Okay. So that would be a stabilizer. But what is the almost? The almost means that all the nice properties are still in a perforated neighborhood of the origin. Basically, origin is not included. Okay. All you can get is continuity at the origin. Okay. This is what you will get out of this result. Okay. Out of this result also, this is what you will get. I mean, for systems like this with no small control property, this doesn't exist, and we've already seen that it is a very tight result. So no small control property, no all continuous stabilizer at the origin. Okay. So if you don't have small control properties, there is no possibility, which is sort of evident also, right? Because usually control flips direction at the equilibrium, right? It's sort of very natural, very intuitive that the control flips direction at the origin, because if you are on one side of the equilibrium, you are pushing it this way, other side pushing it that way. So very natural that if you are on the left, you are pushing right, on the right pushing left. Okay. So I can think of this for aeromechanical systems with position, velocity as states, but same thing can be thought of in electrical, biological systems also. One side of the equilibrium push one way, other side push other way. Yeah. So this actually gives you a way of constructing an almost C infinity stabilizer, which means that it is smooth everywhere but at the origin where it is continuous. Okay. So that's what you can sort of achieve with this Einstein-Sontag formula. I will just show you what the formula is very quickly and then we will end. Yeah. So, in order to give the control, they use the of course the whatever elements are given to us, which is the vector fields, the control Lyapunov function. So, you construct an A of x which is here, which is coming from del v del x f0, which is the drift vector field. Yeah. Then you have a bx which is basically the vector consisting of all the control vector fields. Okay. So, as you can see, this will be a matrix. Okay. What will be the dimension of this guy? What do you think is the dimension of Ax? How many states? N states. Okay. So, what is the dimension of del v del x? Huh? No, del v del x. V is what? What is the dimension of V? I mean, V is what? V is scalar valued. Okay. So, partial of V with respect to x, what is the dimension? Yeah, you can say n cross 1, or typical convention is to say 1 cross n. Yeah, you think of partials as row vectors. Del V, you write it as del V del x1, del V del x2, del V del xn. Okay. Typically, this would be your 1 cross n vector. Okay. What is the dimension of f0? N cross 1, right? It is just a vector field, n cross 1. So, dimension of A? 1. A is a scalar. Excellent. Similarly, dimension of del v del x fix? 1. Okay. So, this is actually a vector then, right? This is actually a vector. Okay. What is the dimension of the vector? It is m dimensional vector. Okay, an m dimensional vector. Okay, great. So, this is what is the Einstein-Sontag universal formula for the control. Okay, very cool control, called the universal formula, or many people just call it the universal formula or the Einstein-Sontag universal formula, but it is one of the few formulae that gives you directly a way of constructing a control if you have a control Lyapunov function. Okay, this will always work. This control is C infinity everywhere but at the origin where it is continuous. So, this will always work. You can take any system, any robotic system, any aeromechanical system, any electrical, any biological system with a model and a control Lyapunov function. This will give you a stabilizing controller. Okay, and that is something super strong, right? I mean, for any arbitrary system, once you have a V, you are coming up with you basically have a formula. Okay. So, hardly do you, I mean, I do not think most of you would know of any nonlinear control formulas, right, that you can just plug and play, right. You can with this. Okay. Looks very ugly actually, for lack of another word, but it is actually quite nice and it behaves very well. Yeah, it is a well behaved controller. Yeah, again because it is C infinity everywhere and it's continuous at the origin. It is a very nicely behaved controller. We will discuss it next time. So, you can see I am using A, I am using norm of B and B itself. So, you have a so basically if you look at this expression, B is what defines the direction of the vector, the control direction. The control direction is defined by B. Okay, and you see there are two cases here, when B is 0 and when B is non-zero. Why? B is 0 corresponds to del V del x fi equal to 0 for all I. That is the B equal to 0, that is how B is defined. So, if del V del x fi is equal to 0 for all I, there is no point in applying a control because control has no effect anyway. So, what is the point? Apply 0 control. Okay. But when if B is non-zero, if you remember what were we doing? We were inverting that particular term, right. If we said that the second, if del V del x f2x is non-zero, then we just inverted del V del x f2 and created a controller. Okay, but that is too basic because you do not know at which instant which one is going to be non-zero. So, this actually generalizes that idea. Okay, you do not know which one is non-zero for that particular x. So, depending on whichever one is non-zero, this will work always. Okay. So that's the idea. Yeah, this is the universal formula, and we'll stop here. Okay, all right.